So on this question, we're asked, first of all, to refer to a point and a pair of vectors from the previous problem. So here's my point P, and there's my vectors v1 and v2. And we want in this problem, first of all, to show that the point P lies on both of these level surfaces. So the level surface with the equation x minus z equals -1, and the level surface with the equation x plus y plus z equals 4. By the way, when I call these level surfaces, what I'm really saying is just that there is a function of 3 variables. So in this case, I'm going to erase this after I'm done writing it. So don't worry about this potentially writing over something in your work. So the function of 3 variables f of x, y, z equals x minus z, and the function of 3 variables g of x, y, z equals x plus y plus z. That these surfaces are being described as what we might call constant loci of these functions. In other words, it's the set of all points. This one is the set of all points in 3 space for which the value of x minus z is all the same. They all have the same value of x minus z, and that value is -1. This surface consists of all the points in x, y, z space that have a common value of x plus y plus z, and the common value that they all share is 4. So that's what I mean when I call those level surfaces. And so the 2 parts of this problem are asking you to do, first of all, the work to verify that the point P that we're being given here, 2, -1, 3, lies on both of these level surfaces. And then also to explain why the line that you parameterized in this part is perpendicular to, explain why this line must be the line of intersection of these 2 planes. So I guess in order to, well, let me ask first of all, what you said you had a conceptual question about part A. So the part A I don't think relies on the answer to the previous question. It only relies on the setup. So what are you interested in hearing more about with regard to part A?
I was talking about part B.
Oh, you were talking about part B. Okay, great.
Yeah.
Um, so yeah, part B. So the question here is, how do we know that the line that we parameterized must be the line of intersection of these 2 planes? So let me start with dropping a hint on line of intersection. So in order to be a part of the intersection of 2 things, right?
Mhm.
Anytime we meet the word intersection in mathematics or logic, we're always saying that it must be something that belongs to both of the things. Right? So, in other words, if we unpack this sentence, the line that you parameterize is the line of intersection of these 2 planes. If so, now I'm thinking about what did I intend when I wrote this question. I think there's a way to do this question without needing to use the discussion about lines and planes that we had that actually belongs to N5 on the homework. That a more general approach to this might be to say the following, that this is the line of intersection of these 2 planes if we could use your answer to N46. If we use that answer, we should be able to show that every point on my line, on that line, satisfies both equations. So it belongs to both level surfaces, both the equation x minus z equals 1 and x plus y plus z equals 4. So that's one way of approaching it that would be sort of less conceptual. I think this would be a pretty computational way to do it, in which you would have to use the answer that you got from part A. The more conceptual way to address this might be to, and I think this is what I was probably intending given the hint that I provided here, the point that the point P you showed in part A here belongs to both of these 2 planes, right? It belongs to the plane x minus z equals -1 and the plane x plus y plus z equals 4. And so, since it belongs to both planes, it must belong to the line of intersection of those 2 planes. And so the real question is about direction. So why would the direction, why would we know that the direction of this line of intersection would be appropriate? And so for this, I'll come back to my whiteboard again one more time here. Here, I think my advice would be to think about this problem once again sort of as, think about what the geometric situation is. So we have one plane here. Let's call this plane P1. Right? And I have a second plane, P2, which happens not to be parallel to this plane. So I don't know how this one is oriented, but I'll kind of draw it like this here. All right, so here are my two planes. Not the greatest picture in the world, but... So here are my two planes, and these two planes intersect along a line, and that's presumably, allegedly, right, the line that we're trying to, the line that would answer this question. So here's my line of intersection. This is L. And so the question is asking, if this is the line that answered the previous problem, in the previous problem, the way that you found a parameterization for this line is that you started with a point P, which had coordinates... sorry, let me skip back over to that. 2, -1, 3. But then in the previous problem, you were asked to find a parameterization for this line, and the information that you had about this line is that it passes through this point, and it's perpendicular to both of these two vectors. And so maybe I'll just ask you, how did you find, in problem number 6 here, how did you find a direction vector? A vector that this line needs to be parallel to. So I think this is the answer to this question will also pretty quickly lead us to the answer to the conceptual question that you're asking about part B. So did you finish number 6, out of curiosity? So in question 6, you picked the cross product of V1 with V2 as a direction vector for the line that you parameterized in number 6. And you did that because you were looking for a direction for this line which is perpendicular to both of these given vectors, both -1, and 1, both V1 and V2, right? And so that's what you ended up choosing as your direction vector. By the way, what was that? What were the components of that vector when you
I
calculated
got
that cross product?
-1, 2, and -1.
Okay. Yes, I believe that. Cool. So if that's the direction vector for the line, let's put that vector back on the whiteboard here. So that means that this line is parallel to that vector, -1, 2, -1. So I'm just going to kind of sketch that in here. So we'll call this V. -1, 2, -1. Okay. So there's my point and there's my direction. But then you, and then the next thing that you did when you were talking about this a second ago was to try and relate that direction to the normal directions to each of these two planes, because these planes are what we're asking about in question 7. And that's the right thing to do, I think, right? Because if this line is really the line of intersection of these two planes, it means that it runs in a direction which is parallel to both planes. Right? This may be another way to think about it.
Right.
This V is parallel to plane number 1, and V is also parallel to plane number 2. But being parallel to a plane means being perpendicular to what?
Perpendicular to your normal.
Yes, being perpendicular to the normal vector to each of those planes. So V needs to be perpendicular to the normal vector to the plane number 1, whatever that normal vector happens to be. So sketch that normal vector into our picture here. So maybe this is my N1. Right? And so V needs to be perpendicular to that vector. little right angle in there. And then the same needs to be true for the perpendicular to the normal vector to the other plane as well. So draw in my normal vector to the second plane, and my direction needs to be perpendicular to that one also. So yeah, you've just talked yourself into the geometric justification. If I want to find a direction for the line of intersection of two planes, because that line needs to be parallel to both planes, it needs to be perpendicular to both normal vectors. And so if I want to
Okay.
find a direction perpendicular to both normal vectors, I should just find the...
By the cross.
the cross product of those two normal vectors, right? That gives me a direction that's perpendicular to both of them. And so it's not an accident, and you've made the connection here between these two problems on the homework, right? It's not an accident that these vectors that you were given in question 6 turn out to be normal vectors to these planes. How can we tell that, by the way? What was the recipe or the shortcut that we learned when we talked about planes yesterday? How do we spot what a normal vector to each of these two planes would be?
We could take the dot product and it'd be 0.
Well, except that what we have here is not a vector. It's an equation that describes these planes. So I don't have anything that I can take a dot product of. Instead, I guess what I'm asking is, what was the... Let me bring up my lecture notes here on planes. All right. Sorry, I just have to click a couple more buttons here to tell my thing where to find what I need. There we go. All right, so when we looked at equations for planes yesterday, we came up with this form, right? That if you give me a normal vector in the components a, b, and c, and you give me a point with coordinates x naught, y naught, z naught, then I can come up with an equation for the plane that passes through that point and has that normal vector, just by writing a times quantity x minus x naught plus b times quantity y minus y naught plus c times quantity z minus z naught is equal to 0, right? And so if you do out the algebra in that, what you end up with is a left-hand side of that plane equation, which is just ax plus by plus cz. And a right-hand side, which is just going to be some number, and that number ends up being the dot product of the point with the normal vector, right? So the right-hand side really doesn't matter. If the question is how to get a normal vector for a plane out of an equation that we're given for that plane, all we would need to do is just take the coefficients of the variables x, y, and z. Right? Those coefficients a, b, and c are precisely the components of a normal vector to that plane. This is just like when you have in college algebra, you're given an equation for a line, and it's y equals 2/3 x minus 6. What's the slope of that line? It's the coefficient of x. Right? Same kind of deal here, that the normal vector to a plane, which also tells us the orientation of the plane within space, just like the slope of a line tells us the orientation of a line within the plane, we can find a normal vector to that plane just by extracting the coefficients of x, y, and z. So bringing that back to the homework question, if I want a normal vector to the plane with equation, well, let's start with this second one because it has an x, a y, and a z in it. What normal vector could I extract? We called this N2 a second ago on the whiteboard. How would I find a normal vector from this equation? What would its components be? Well, what are the coefficients of x, y, and z in this equation? For this equation, they're just all 1s. And so a normal vector for that plane would just be 1, 1, 1. We could also use any scalar multiple of 1, 1, 1 that we want to, except the 0 scalar multiple. But the easiest way to do it, right, the quickest path is just to take those coefficients out, and those coefficients form the components of a normal vector. And so if 1, 1, 1 is a normal vector for that second plane, what would a normal vector for my first plane be? What are the coefficients of x, y, and z in this first one? My head out of the way.
1, 0, and -1.
Yeah, 1, 0, and -1. Why is there a 0 in there, by the way?
Because there's no z term, so we assume 0z, or no, 0y, 0y.
Yeah, right, exactly. There's no y appearing in my equation, and so we could sort of force there to be a y by adding a 0y in there. So yeah, again, if we wanted to be brutal about it, 1x plus 0y minus 1z. And so that's where we get the coefficients for that normal vector. Right. And so that, I think, sort of gives the geometric description of if we didn't want to sort of directly use the answer, the parameterization that we got in question 6, and just stuff that parameterization into both of these plane equations, then a more geometric way to do it would be to say, well, the normal vectors to these planes were precisely the two vectors that we took the cross product of to find the direction of our line to begin with. And so that must mean that my line runs in a direction parallel to both planes because it's perpendicular to both normal vectors, right? And so that sentence, I think, would be, one way that you could explain the conclusion of part B. That this line must be the line of intersection because it contains a point which belongs to both planes, and it points in a direction that is parallel to both planes. And therefore, it must be the line of intersection.